Hi everyone, welcome to the lecture series on structural dynamics. In this present lecture, we will be talking on the numericals on damped free vibration specific to single degree freedom system. Here we take one example of problem where the mass of 0.970 kg is attached to the end of a spring with a stiffness of 7 Newton per centimeter, and we need to determine the critical damping coefficient. So the solution goes as follows. So first, since it is asking critical damping coefficient, which is C, and we also have a relation C by 2m equal to xi omega. Xi is the damping ratio, but when he is saying critical damping, that means xi equal to 1. When xi equal to 1, the C will become 2m omega. This 2m goes this side. So simply the mass is known to me, and I need to find a frequency which is requires stiffness, which is 7 Newton per centimeter. I can convert this into Newton per meter, so I need to multiply by 100 because 1 centimeter is 100 centimeter is 1 meter. So 700 Newton per meter. So the mass is given as 0.907 kg. So substitute in the critical damping, because before that find the natural frequency, which is root over k by m. K is 700, m is 0.907, we get 27.78 radian per second. And once I know omega, natural frequency, and the mass is given, so I can find critical damping coefficient, which is 2m omega. So I get 50.39 Newton second per meter. So let us look at the next problem, which is a damped vibration record of a spring mass dashboard system shows the following data. The amplitude of second cycle is 12 millimeter, amplitude of third cycle is 10.5 millimeter. He could see only the two amplitudes, second and third. And the spring constant, which is stiffness, is 7850 Newton per meter. The mass of spring is 2 kg. Mass attached to spring. You can correct as mass attached to spring. Mass attached to spring is 2 kg. Determine the damping constant, that is C, assuming it to be a viscous damping. So solution goes that I know the x2, I know x3, the ratio gives me logarithm decrement, which is ln of natural log of x2 by x3, so that comes out to be 0.133. I also know the logarithm decrement is related to damping, which is 2 pi xi, assuming the damping ratio is small. So here, because I got the logarithm decrement is very small value, definitely I will have damping ratio less than 10%. Otherwise, I will have to have this divided by root over 1 minus xi square something feature if the damping is more than 10%. Right? So the xi become delta by 2 pi, that is this, and you get a 0.021. That means 2.1%. It is less than 10%. So I could assume this formula 2 pi xi. As I told you, otherwise I would have taken another the denominator factor of under root of 1 minus xi square. So now I got the xi, right? So I need a damping constant, which is C, right? C by 2m. This is damping ratio. The stiffness is given to me, mass is given to me. So the natural frequency I can find out, which is root over k by m. So I get 62.5 radian per second. So the damping constant is related to the xi omega is like this. So C will become 2m xi omega. So I know the xi, which is 0.021, and omega, which is 62.5. Substituting here, I get damping constant as 5.32 Newton second per meter. So this is how we will solve the problem of logarithmic decrement and damping constant. So look at the next problem. A mass of 1 kg is to be supported by a spring having a stiffness of 9800 Newton per meter. The damping coefficient is 5.9 Newton second per meter. Determine the frequency of the system. Since damping is given, this frequency will be damped frequency, we should understand. It is not undamped frequency. Find the logarithmic decrement delta and also the amplitude of third cycle if the initial displacement is given as 0.3 centimeter. So let us see the solution. What are given to me? The stiffness is given to me, damping coefficient is given to me, and mass is given to me. With the given things, what I can find out? Since he said damping is present, the frequency of system will be a damped frequency omega d, which is different from omega n, or natural frequency or undamped natural frequency. Okay, so I know the relation, the damped frequency omega d is omega times under root of 1 minus xi square. Xi is a damping ratio, so I don't have damping ratio. So to find damping ratio, I have relation xi equal to c by 2m omega. And how to find omega? Under root of k by m. Once I get omega, substitute here, I get damping ratio. Once I get damping ratio, substitute here, I get omega d. That's what he is asking. Very simple. We start with the finding omega, which is root of k by m. M is 1 kg, which is 31.3 radian per second is my natural frequency omega. And then damping ratio c by 2m omega. C is 5.9 and mass is 1 kg. Omega is 31.3 radian per second. I get 0.094. That means multiplying by 100, that is a percentage conversion. So 9.4%. Okay. So once I get this xi, so I can find the omega d. Right? Omega into under root of 1 minus xi square. So I get 31.2. See how much? Not much reduction. It was 31.3, it is 31.2 radian per second. It is not much difference in the undamped natural frequency to the damped natural frequency. So that is why if your damping ratio is less than 10%, we don't have to much difference between undamped natural frequency to the damped natural frequency. So once I get the omega d, so what is asking? The logarithmic decrement. For the logarithmic decrement, formula is delta equal to 2 pi xi. So xi is known to me, is 0.094. So I get this 0.59, and this delta, since he is asking me to find out, this is logarithmic decrement, what he is asking, I got it here. And since asking the amplitude of third cycle, so I have a relation of logarithmic decrement with the amplitude of different cycles, so which is delta equal to 1 by n, because he is asking third cycle, and I know the initial displacement 0.3, so x naught is known to me, so 1 by n ln of x naught by xn. So substituting here, which xn will be the nth cycle, which is third cycle amplitude. So I can find out, taking 3 this side, 0.59 into 3, right? So then e to the power, that becomes 1.77, e to the power of 1.77, and 0.3 by x3 means here. So from this I can find x3, which is amplitude at a third cycle, equal to 0.05 centimeter is the amplitude at the third cycle. Suppose it is asked fifth cycle or fourth cycle, simply this will be my n will be my 4. Everything else remains same. Okay. So we will go to the next. The mass of 20 kg is suspended from the spring of stiffness 39,240 Newton per meter. A dashpot is fitted, and it is found that the amplitude of vibration diminishes from its initial value of 25 to 6.25 millimeter in 2 complete cycles or oscillations. Find the resistance offered by the dashpot at a velocity of 0.3 meter per second and the frequency of damped vibration. He is asking two things: resistance offered by the dash part, that means FD, and the damped frequency, which is omega d. So solution goes, FD is C times dx by dt. We can also write as x dot. This can also be written as x dot. And I also know the relation, the damping factor is 2m omega and xi, and omega is, I know, root over k by m, and the delta, which is logarithmic decrement, is 1 by n times ln of x naught by xn, because he is asking here the two complete cycles, means n equal to 2. Okay. So from initial 25 to 6.25, so 6.25 is the second cycle, x naught is initial, the first one, and 0th one. And I also know delta is related to the damping ratio. So we start with logarithmic decrement, which is known to me, which is 25 and 6.25. So 25 by 6.25 natural logarithm, I got delta 0.693, and the damping ratio I will get it as 0.11, that means 11%. It is slightly more than 10%. Still I can use that relation here. Otherwise I should use delta equal to 2 pi xi by under root of 1 minus xi square, where I know delta, so substitute this delta of 0.693 and square both sides, and I will get a quadratic equation in terms of xi square and find the xi value. You may get a little, maybe 0.15 or 0.16. Not much difference there. Okay, but we have your option. Okay, so natural frequency omega equal to root over k by m, which is 44.3 radian per second. The damping constant is 2m. I got xi is there, omega is there, so I get 194.9 Newton second per meter, and the damped frequency omega d equal to omega into root over 1 minus xi square. I get 44.03. See the difference? 44.3 and 44.03, very less, 0.27 difference. That means damping still less, 11% is not much. So the damping resistance, which is Fd, nothing but C into x dot. The L velocity is given to me, dash part velocity at 0.3 meter per second is given to me. The C is damping coefficient 194.9, so 194.9 into 0.3 gives me 58.47 Newton. So the next question goes, a machine of 20 kg mass is mounted on a spring and dash part. The total spring stiffness is 10 Newton per millimeter and the total damping is 0.15 Newton millimeter per second. If the system is initially at rest, that means initial displacement 0, and the velocity of 100 millimeter per second, that means initial velocity is given, is imparted to the mass by hitting, then the determine displacement and velocity of the mass as a function of time, x of t and x dot of t, and also we need to find out displacement and velocity are the same at t equal to 1 second. So this is solution where given things, mass, stiffness, which converted into Newton per meter is 10,000, and damping factor, which is 0.15 millimeter per second converted into meter per second, which is 150, right, Newton per meter per second. And the initial condition given here is initial velocity. So displacement is 0 at time t equal 0. At time t equal 0, velocity is given as 100 millimeter per second, right? So I need to find out x of t and x dot of t. To find this, I need to know the response at a damped vibrations. For that, I need to know the frequency, natural frequency, root over k by m, which is 22.36 radian per second, and damping ratio, because damped vibrations, damping ratio is required, which is 0.1677 or 16.77. It is more than 10%. Okay. Now, the response of the free vibration of damped system is this. This you can write sine also. If you write this as a sine, then it will be sine omega t plus phi. This is what I gave you for the derivation. Okay, either sine omega t plus phi or cos omega t minus phi. In this case, either way, entire remaining response remains same. There is no change, nothing to worry. Okay, so applying initial condition. What is the first condition? My displacement at time t equal 0 is 0. So this displacement 0 equal to, when t equal to 0, this term is 1, a is a, and t is 0, that means cos of minus phi. Cos of minus phi is cos phi. So when cos phi is 0, so phi will be 90 degrees, pi by 2. Okay. Now, then velocity, because I have another initial condition. Velocity at t equal to 0 is 100 millimeter per second. So differentiate this displacement one time. So I displace one. So this function by parts. So this is one function, this is another function. So first function differentiation into the second function, then second function differentiation of first function, second function. So I got this differentiation, right? And substituting t equal to 0 and velocity is 100, t0 means this is 1, t0 means cos phi, phi 90, so entire thing is 0. This is sin phi, sin of minus, minus sin, so minus into minus plus, sin phi, sin 90 1, so omega remains. So the a will become 100 by omega, omega is 22.36, so a will become 4.47. So instead of a, you can write rho, anything, it is just amplitude of the maximum amplitude of the damped vibration. Okay. So now I got the coefficient a and phi, and I simply substitute here, I will get a x of t, and substitute here, I get a velocity. And then the second part of the question is substitute t is equal to 1, and I will get a displacement at t equal to 1, and substitute here, I will get a velocity at t is equal to 1 second. Very simple. So let us see this. So this is a displacement function with respect to time, substituting this a and phi. So this t equal to 1, substituting here. So in terms of t, right now t is not to be substituted, simply phi and a. So a is 4.47, xi omega, xi is 0.1677, omega is 22.36, so multiplying we get a minus 3.7, and here cos of, I will say minus of pi by 2 minus 22.360, cos of minus is minus cos, cos, so pi by 2, cos pi by 2 means sin 22.36. So when substituting at t equal to 1 second, this is the first part of the question, displacement, and this is second part question where time t equal to 1, I get a response of minus 0.04 millimeter. Similarly, go to the velocity in terms of t, this one. So write in little crisp form, this is in terms of t, and I can also substitute xi and omega, and I also substituting t equal to 1 second, I get this. Only care you have to take while substituting in the sine or cos, here this phi or omega are in terms of radians per second, radians. So we need to convert into degrees if you are using calculator setting of degrees, or you have to change the calculator setting to radians. So this value will be minus 2.16 millimeter per second. So this is the velocity, and here is the displacement, right? So this is what at a time t equal to 1 second. So these are the problems as a homework. You can try to solve same line. I just change the values so that it becomes for you a practice. Thank you.